Test. Test, test. Alright. I think I got audio now. Alright. Alright, so, I'm working on a tiny little operating system. So, let's see. This, there's this guy, Seiya Nuta, who wrote this book, and it's how to make a tiny little operating system. I've been following that to learn, you know, how it works at all, and trying to branch out and just do my own thing from there. So, right now we're working on having a file system. So the idea for this little operating system is, I think this is a little loud, isn't it? So for this operating system, we're using Kimu to, you know, as a virtual machine, and what's called a Virtuo block device, which, you know, works the same way that like a physical, at least the way you interact with it, like you would a physical disk, right? Okay, but sorry, my dog is freaking out. Hold on. Alright. This little dude barking at everybody. Alright. I should probably flip the window here since my face is down here. Alright. So yeah, you have this like virtual block device. Read and write to. What I'm trying to work on now is a file system. So in the book, he uses this really kind of interesting setup for a file system where you basically use a tar archive. Like, doesn't tar stand for tape archive? But yeah, you use tar file format for your entire file system. So right now, I have basically in this directory, you're gonna put all like your file system. So right now there's 2 files, just 2 text files, and then so you know, use tar to create an archive of that. Right here, right? So you create this with all the text files that are in that directory, and plug that into the drive in Kimu. So right here you can see that it's using the disk.tar file in drive 0, and that's where the virtual block device is, which will you know, read that in a raw format. So like, it's just the raw bytes of tar format, which looks like this. Let me pull this over. Alright, so you basically have a bunch of headers and then the data that follows it. And in the header, you have these fields always, and then there's different kinds of tar format. U-star is the one that we're using. So U-star has these additional header fields. You know, so you have stuff like the name of the file and different stuff in there, and following the header is the data. So yeah, so like this is basically what the format looks like. And since we're reading it in like raw format, we can literally just take that memory and like cast it to this type. Yeah, so the question becomes like, all right, how do you build up like an in-memory representation of a file system so that it's useful, like, and furthermore, like, how do you access that and interact with it like in user space? And I'm you know, confronted with thinking about these things for the first time. I've never wrote a kernel ever until now, and so I guess I'm like pretty naive. I don't really know what I'm doing. So in the book, he does it sort of. I mean, it's a learning resource, right? So he's just doing a super simple thing, but like he has like just a flat array. This is the disk, and you know, pre-allocate a size. And it's also weird because like the size he uses is dependent upon. Like he also has files, right? So you have your representation of what a file is, which is just like, you know, the name, size, and the data. This is like what I'm gonna use, and he also stores it like each file owns the data, so it's a fixed size as well. And super simple, but like doesn't actually work for, you know, a real operating system. I hesitate to say real because like mine's a toy version too, but whatever. It's like it's not wise. Like for example, what's the file size max? 32 3 kilobytes. So that means like every single file that you store is gonna pay for that memory, even if it's like a 1 byte file. Anyway, I'm just trying to figure out how I should actually do this. So, you know, when you boot to the kernel, what does it do? Well, you know, you set up a stack pointer and then just jump into this kernel main. It's gonna clear the BSS section, set up the trap handler, initialize the block device, and then initialize the file system, which is basically just gonna like, you know, read through the entire virtual block device. You want to read through the headers of all the files like in tar format. You know, so you have all the metadata basically about files. Currently what I'm doing is literally reading all of that data into memory, so the disk like is in memory rather than non-volatile memory. And I just want to do it slightly better than that. Like I don't think I'm gonna have like great ideas right at the beginning, but it has to be something where like it doesn't matter the size of the file, it can still operate fine. And furthermore, after this, you're gonna want to be able to like have system calls to read and write to these files and like create new files and stuff. So we're gonna start doing all of that shit. Okay, so currently we have a hard-coded disk size, which we're gonna change. So what I'm thinking is like, so we can query once like, so the virtual block device has like these registers that you can read from, and the mode that we're using we're using in this like MMU mode. I mean, it's probably worth finding like the virtual spec. So this is the spec. There's like a MMU. IOMMU. like control registers. Here we go. MMIO, I guess. Yeah, so like you can read and write to these registers to control the thing. And so you can query, like read from this register, like, you know, how big is this thing? So I think what I'm going to do is have like a max disk size and just let the virtual block device drive like how big the disk is going to be. And if it's bigger than our max, then we'll just panic. We do need to align it to sector size, so 512 bytes is a sector. And how big should we allow? Like 2 megabytes to start with, like tiny little disk. Start with that. I don't think I have megabytes yet. Let's... Okay, so 2 megabytes, disk size max. So this num sectors is what we've read from the block device. So this is how many sectors are on the like hardware. I need to like my terminology down. It's weird because like that's the disk, but then we have like our representation of the disk too. So I don't know what to call it. I guess I'll just call it like the virtual. Well, that's weird too, because if I call it the virtual disk, mine's like the virtual disk. This shit is so bizarre. But anyway, that's how many sectors we are. So we need to like allocate memory for the disk here. Alright, so step 1 is going to be, instead of having a like static sized disk and memory, we're going to dynamically allocate disk and memory. So where's disk now? Right now, we're gonna make it just a pointer. And then I guess we're gonna need disk size. Should we store the size or the number of sectors? I don't know, my gut's telling me we should do sectors, so... Disk num sectors. Well, I guess that's the same as this, right? Alright, we'll do that. So, we're just going to allocate pages for that. How many pages? So, however many sectors there are, hold on, what's my, so you can just, you want to say how many bytes divided by the page size, I guess. So it's like that many sectors times sector size divided by page size. I have that right. But you need to like round up, I guess. So it's that, but let's align it up to page size. Should I do that before or after the divide? Does it matter? I don't think it matters. Get the same result. No, we do want this. So you align that up to page size and then divide by page size. Alright, you want that many pages. But we want to check if that's bigger than... Alright, let's save this out. Device size. God, variable naming is hard. That'd be 64. Let's do 32. If device size is greater than disk size max, well, then we're gonna panic. Alright. I'm still struggling with how to talk about these. Like, how do I talk about the difference between, like, my memory representation of the disk and the virtual block device representation of the disk? I don't know what to say. Because it's like, alright, well, the disk size is this, but the device size is that, I guess? I don't know. Disk max size is this many bytes. But... disk size max device size. Alright. Alec Pages returns just a physical address. So I guess we need to cast that to UA pointer. Okay, so now you've allocated enough memory for the disk. Which is interesting that now disk is like aligned to page size. I'm thinking maybe the disk should be like sector size aligned so that when we are gonna go right out to the block device, we can just dump the memory directly. So, damn, does that mean it needs to be aligned to page size and sector size? Well, actually, this isn't aligning it to page size. It's just saying like how many pages you need. Alright. I'm just not gonna care about that right now. Alright, so you've allocated enough space for the disk. Now we can read it into memory. So let's just do one step at a time. So, oh sorry, I should be writing over here so it's easier to see. So a file still owns that. Everything else should work fine then, right? All we did was... Did we delete the... Yeah. Right, so... Yeah, so this is what I was thinking. It's like now we have a disk size max, but we don't really have like the actual used size of it. So, but we do have the number of sectors. Actually, we have it here, it's device size. So like that's how much memory is actually used. Sure. Okay, so it seems to be working fine, right? We can test this too if we just let's just print out the file data too. Yep. So this is the FOF file, this is the Jabberwocky file. Cool. So now what we need to do is fix, like, the file should not own the memory for that. Because what I'm thinking is, like, on file system init, like when you boot to the kernel, you're going to initialize the file system, which is just going to read all of the metadata about files. So you want to know the name of the file and like how to access the data such that like in user space, if you want to load the file, at that point you can read the data. But what I don't know is if I should just stick with the like dead ass simple approach of like write at boot, read all the memory, like the disk into memory fully. So it just seems so wrong. It just won't work if you have like a lot of files. Also, like, I don't know how I'm gonna be. I don't have a good picture of like the usage patterns and things, so maybe I should just like push forward and then it will become clearer what the right thing to do is. So what I was initially thinking is like, we'll just have a pointer to the data and maybe like a, like is loaded. And so, um, like is initially false, and then whenever you try to use the file, if this is false, at that point you load the data. That might be the way to go. Because right now we're copying the data in there. So, you know, the first thing I initially did was, like, I just made this a pointer to the data, and so you're already reading it, like the tar format has the header and then the data, and so I'm reading that in already. I already have the data read into memory. So if in the file struct you just point to that, then you don't have to copy the data out. But then the problem comes when you edit that file, right? Because now, you know, you've read it in this tar format where you have header data, and the data is fixed size, so there's no room for more. You know, like what you could do is just, once you've read the whole tar into this disk, so like once you've read into this and this has been initialized, well at that point you don't really need the tar format anymore. So you could now basically treat this as an empty buffer, and you know, when you need to write out to disk, then you could treat it as a blank buffer, fill it up with like your new formatted tar format to write out to. I'm in one of those situations where, like, when I tried to, like, think about one problem, like, 12 more questions arise. So, this file is our, like, in-memory representation of a file at any given time. So, I'm thinking we just need a pool of data for file contents. Sorry, a pool of memory. So So how do we control that? And when do you allocate that memory? Because like at this point, you don't have to do this. You just read the metadata, and it's just like, you know, I know the file, I know the size, but you do need to know like where to get the data when you want to load it. So you would at the minimum have to do something like this, where you say like, here's where to get the data when you need to read it out. Which is also weird because right now this is in memory. Like you've read the whole disk into memory, which is like not how a like file system would work, right? I feel like what you would need to do is like maybe store like sector, but that doesn't work either because that doesn't guarantee that it starts at that sector, right? It just means it's somewhere in that sector. So you need like a sector and an offset, I guess, which at that point it's just the pointer, right? But well, no, yeah, it's not. I guess you'd need a sector and an offset. How do you know the offset though? Too many things to tackle at once, so we're going to eliminate some of them. Right now, we're just assuming that we're reading the disk all into memory, so we can solve that later. So, boom, we're just going to get a pointer to it. Right, so that's where you find the data when you need to load it. For the file, we're going to say you have a is loaded, which is false to start with, right? Right. Okay, we store the pointer. Great. That shouldn't have broken anything. Still good. So, alright, let's move on a little bit. So, let's check out, so what he's doing. You need to be able to write to disk back. So the idea of that is to, you know, go through all the files, write those back into this disk buffer. So yeah, that's exactly what he does. He like reuses that as space to. So this is assuming no like changes to the size of files, which we'll stick with that assumption for now. So, blush. So, what do we need? Oh shit! What do we need to do? Jesus Christ. Well, basically need to write all files into tar format in disk. Right, so you're gonna loop through all the files. What do we use? Let's use int. Files max. So you get the file out. Yeah, so we're gonna be writing this format out. So I guess you need one of these tar headers. I'm gonna call this H. Header name. Mem copy, header name, file name. Right, I can do that because it's an array. Right. Yeah. Name. Mode. So, I didn't write this, but I should. This is like octal string, kind of, like. So yeah, these are in octal mode and they're like string. File sizes too. Yeah. I wish I had a thing that was like, hey, align all this shit to this. So far, best I can do is something like this. Okay. So, permissions, what is it? Like, what is it, 664 or something like that? Unix file permissions? I feel like it's 644 or 664 or something is like the common one. Fucking, I don't goddamn know. 664, 644. What is this? User read, write, execute, group read, others read. Oh, no execute. So read, write. I think that's it. Yeah, let's just see what does say I do. Can I do that if it's an array type? Eight characters. 1, 2, 3, 4, 5, 6. What? I'm confused now. Right, you can't really do that. I have to do like a stir copy. Which I don't have yet, as you can see here, so I guess it's time to go implement that fucking thing. It is time. Alright. Let's check the old... stir copy. So... best source. I don't give a fuck about const. Stir copy. So... this thing just assumes these will have enough space. Which one? Does it say which one you use to like... alright. Copies the null terminated byte string pointed to by source, including the null terminator, to the character array whose first element is pointed to by this behavior is undefined if this is not large enough. So you're just gonna assume this, so... we'll just say start at source while that is not 0, so I guess you can just do that. I see. Well, you can't really use the pointer because you need to... nope, I had it fine. We'll just also store... there's that. That and that. Okay. Oh, wait, I'm stupid. I just do this. We just do this. Yeah. Duh. Alright. You just do that. And what, you return a copy of this, probably? Well, you return a copy of the pointer. Jesus Christ. Okay, we have stir copied, I think. Except not, because you need to include the null terminator, so we do int I, boom 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 boom. So once you've reached the 0, yeah, alright. Now we got stir copy. So before we do any of this, let's just make sure that that shit works. So blam. Hold up, what? Oh, that. Do that work? It do. It do seem to work. So we can switch that. Store copy is unsafe. Never use it. Never use it ever. So for mode, we're gonna do this. Huh. Okay. UID and GID? I don't fucking know what to do with those. I'm gonna ignore them. Size. Gross. You need to have like some octal. Like I have U32 from octal. Now I guess I need like octal from U32 and it's a string. That's kind of gross. How should we do that? We have U32 from octal. I guess we need to like reverse that. It's not really octal though, it's like octal string. Alright, so you pass it the U32 and a pointer to write it into. Do I need to include the length? Maybe. Yeah, so I basically need to reverse this process, kind of. Like, how does octal work again? It's gonna be, each digit is, there's 8 possibilities, so... How would you do that? So for example, what does, like... If you had 644, like we have over there, how do we get the decimal representation of that? Well, it's like this times, that's how many ones there are, that's how many eights, that's how many, like, 8 to the power 2. This would be like this. 6 times 8 to the power 2 plus 4 times 8 to the power 1 plus 4 times 8 to the power 0. Can I do this? Yes, so actually I might be able to just literally. $420? No fucking way. That represents 420? That doesn't seem right. Cool. Alright, since I'm a fucking idiot, I don't trust myself. Let's double check. Octal to decimal. It is 420, okay. So I'm only a little bit of an idiot. So, if you have 420, how do you turn that into octal? Well, you know, you're kind of like, how many 8s go in there, right? Is that how it works? Alright, so if you... my brain is struggling to understand this. How do we turn this decimal into this octal? Well, I mean, I know you could do like, alright, well, how many like 8 squares does it fit in? But like, the question is like, how do you know where to start doing that, you know? Because for an arbitrary number, it could be way up here, so it's like... You need to know where to start doing that? Is there a way to build it up in reverse? Like... I feel like there's a better way to do it, but all I can think of is this. Like... All I can think of is this, right? So you start with, like... It's not really digit, it's like... I don't know, power? Yeah, we'll do this. Power equal 1. Right? What that should give us right now is power 2, I guess. Or rather, this will give us power 3. So you're checking the next one. You're like, does the next one work? Yes, increment it. Okay, so at this point, power should be equal to 2 for this number. So now we can say while it's greater than or equal to 0, we do this. We say well, this value at power index is the string representation of this number divided by 8 to the power. Wait, it's... Damn, we don't even have power, do we? Because we don't have a math library. So do I have to make a shitty, like, POW thing? Gross, I think I need to make a disgusting POW thing. Maybe don't do that. So that's the digit, right? So you need to do that. Plus 0. Mm-hmm. What do we do? Just panic on failure? Because, like... So it's like if power is greater than ln? Yeah. Power is greater than length. I guess we just panic? U32 of that. not fit in octal string with length. That. I guess we do something like that. So this U32. Fuck. I guess we'll have to do it in this format. The fuck just happened? It was weird. Alright. So that should work. Except for the fact that... Alright, what's up? Something's wrong. Why is this freaking out? Oh yeah. Okay. Let's test this out. So if we take 420 buff, yeah. Ooh, I guess we do need to null terminate that. So we'll do that. Because you need space for the null character. Interesting. So it's gonna like... Yeah, bizarre. So you kind of need to offset the whole thing by 1 so that you can put the null character in. Or alternatively, what you could do is just memset the whole fucker to 0, but then you need to write actual zeros in there, not null characters. So I mean, you can do all this stuff before you do it, and then you say memset this to this character, this many of them, then ah shit, this goes from left to right though, and you're like rendering from right to left, so it's even worse than that. So what do? You have like a... So it's actually this? Alright, so if you have a thing... So you have 6 characters. So power is starting at 2 in this case. But the index is 3. So it's length minus 1 minus power. Yeah, that'll flip it and give us this. Right? But since you need the null terminator after it, it's like you actually need to put it one more. So it's like length minus 1 minus power minus 1. So length 6 minus 1 is 5, minus power in this case was 2, which gives us 3. But you actually want here. Then the next one you have, so this would render the 6 here. Next one, power is 1. It's like you want it to go right there. Like that's a 5. Minus 1 is 4. Minus 1 is 3. Minus 1 is 2. 0, 1, 2. That gives us the same thing. That's not right. Minus 1 is here. So that is right, actually. You're right. Whew! Sheesh. Okay, so now what you do is the last one is you actually put a null character in there. Okay, that should actually do it. We'll do that and just panic. Here. Cool, so now we just need to implement power. I suppose for now we can just do crime. Uh. Alright, so to the power, if it's 0, return 1. So I guess you could do this, right? Results 1. Well, it's less than power. You just do results times equal to base. We return result. So you start at 1, so I don't know, 8 to the power 0. We return 1, 8 to the power 1. Yeah. 8 to the power 2. Will not fit an octal string with length 12? What are you talking about? Hmm. How the fuck is power 420? Huh? Actually, I guess we can start here. Alright, so power 0. While U32 divided by power plus 1 is greater than 0. That's why right there. God damn it. So stupid. Okay. What the fuck is happening there? So we're stuck in an infinite loop somewhere? It's gotta be this, I guess. Ah, gross. We have to use a different fucking terminal, so this terminal doesn't understand these fucking codes, so I have to do this. Alright, Yeah, we'll just run it here. Where the fuck are we? So we're here. So just where the what the fuck is it? This location? Add shift left branch if not equal to where? So we're definitely in an infinite loop. Where the fuck are we? I guess we have to be in this one. Ugh, okay, this is my problem. It's fucking unsigned. Alright. Honestly, a lot of this would be solved if the power is just an integer. So maybe we'll go with that. And so it's 0. That'll cast it to U32, but I'm totally okay with that. Should we make the length an integer then? That makes that comparison fine. Sure. So stupid. Alright, well, I mean, you got a 6. That seems good. But it's definitely fucking broken, so... God, I wish I had a fucking debugger. It's so shitty when you're working on kernel shit and there's no fucking debugger. So I can't just step through my fucking code. Should I just do it around the whole ass thing? Is that my problem? It's not my problem. 652 and 420. That ain't right. Right, so we need to keep decreasing the number now. So it's like this. Uh-huh. Ugh, God. This is like such a stupid thing to like spend so much time on. So, I mean, the first time, right, it's 420, right? You divide that by 8 squared, you get 6 with some remainder. And I guess you want to keep the remainder? So, I guess you need a divisor, which is this fucker. And then U32, like you do mod equal divisor. Alright. Yep, there we go. 644. Wow. Gross, very gross. That was bad. That made me feel very shitty. Alright. We need to figure out how to calculate the checksum. The checksum is calculated by taking the sum. Damn. So you take the sum of the unsigned byte values of the header record with the 8 checksum bytes taken to be ASCII spaces. What do you mean? It's calculated by taking the sum of the unsigned byte values of the header record. With the 8 checksum bytes taken to be ASCII spaces. Decimal value 32. It is stored as a 6-digit octal number with leading zeros, followed by a null, and then a space. Okay. Well, okay, so calculate checksum. Hold on, my dog's freaking out again. Okay. Okay, let's keep going. What we got, buddy? Shigumi. Alright. So, we're calculating the checksum. It's just like summing up all the bytes, I guess? How many bytes are in that thing? I don't know. Hmm. I guess you can just say... size of the header. I guess it's like, you interpret it as an unsigned byte, and it's just... But what do we do about this thingy? That's technically not part of the header, is it? It's not, right. Well, it's gonna be a 0, so that's fine. Okay. So we just do that, and then it's also saying for the checksum to like treat all of the... With the 8 checksum bytes taken to be decimal value 32. So I interpret that as saying like, alright, this. Eight checksum bytes, which are taken to be ASCII value 32. Uh-huh. Is stored as this, with leading zeros followed by a null and then a space. What the fuck? So how am I gonna render it like with the extra space? I know. You just make it like a 5 buffer. Yeah. Alright. So we did that. Should we do this thing where we treat it assigned? Nah, fuck that. Yeah, we're stupid. That's not actually the checksum. Octal from me 32. Checksum. Oops, H header. Yeah, so here's what we're gonna do. The checksum is 8 characters. It is stored as a 6-digit octal number with leading zeros followed by a null. Six-digit followed by a null and then a space. So you do 7. And then you say checksum at 7 is a space. I fucking love this song. Okay, so what I'm doing now is I've hopefully calculated the checksum correctly. We have to do that after we fill out the whole header. Then copy the header out and then the data right after it. Right, and then we're going to write all that to disk. One thing we want to do is we only do this if in use. Uh-huh. Interesting. So now now we're depending on like the actual disk size. So num sectors, well, we're gonna have to line up. Right, so you have some offset. This offset's gonna keep changing, so like disk end. That gives us the size. Line that up to sector size. Yeah, how are we gonna get the end? Yeah, these don't have to be 64. The only reason this is 64 is because this requires it to be. feel like I got broken shit. But let's see if it even compiles at all. Do not. Wait, what? That was weird. Right, so you go to this location. Alright. So we're gonna take that, treat it like a byte pointer, and then dereference it. Okay. But of course we're not using that yet. So before we do any of this stuff, we're just gonna file system init and file system flush. Alright, so it's writing out. It's just seems corrupted. Not an archive. I wonder why. Well, it's interesting because the size is exactly the same. Oh, we don't fucking update the offset. That's probably a big fucking reason. Right. Still corrupted. So it's really close. There's just some missing fields, I guess. Interesting. Hold up. What's actually pretty interesting is this. It is actually working, right? Because the fact that we're running this and it can load all that stuff and then run it again and it can still load it. It's loading and saving. Check this out. We can verify it too. So if we do this and actually I'm gonna switch up the music. Alright, if in Flush, like before we do this, so we write all the data in there and then let's override a little bit. Put some recognizable string in there. Oh. Sick band. Alright, so what should happen, which we expect to see is like we run it the first time and let's print out the file data. So when you init file size and data. We should run it and it'll print out the original and then we run it again and it should print out with the power trips in it. Shit. There's a warning. I think I just fucked everything up. Oh, that's fine. It's just a different kind of pointer, I guess. Right, so it's printing out like this. If we run this again, we should see the power trips. And we don't, so it's not working, I guess. Unless this is just... Hold on. What? It literally is writing this in there. I'm confused. It wrote the power trips. So how come when we load it, it's not there? Oh! I know what's happening. Shit, my contact just fell out too. Hey, buddy. Hey, bud, what's up? Hey, sweet boy. What's good? So the problem is we're just recreating every time. Stupid. Check it out. If I were to do this... Don't... Oh. If we don't do that... If we don't rebuild it, it should work. Power trip. And actually, the reason that it's only printing one is because by using stir copy, we've inserted a null byte. And so it kills like literally the rest of the entire thing. Just dropping a 0 in there. Alright. But we can write to disk. The interesting thing is like it's no longer in a tar format that's readable by Windows. So I guess Windows needs all the fields and we're only filling out some of them. So that's the thing. Alright, that's cool. That's like a small win. So all this logic is sound at least. Now I'm not sure if I should. So I'm interested in filling out all the fields so that Windows can recognize this. Yep. Interesting. So this is all getting the stuff that I was sort of thinking about, which is like right now this is all happening in kernel space, right? We're reading the lock device into kernel memory, but where all this stuff is going to be used is in user space. For example, the only user space program so far is a shell. And so in the shell, you might have a command like read a file. So it needs to access memory that's in kernel space. So what's actually gonna need to happen is like when you do a read, maybe at that point you load the file into user space memory, like you map it into user space memory. But anyway. I need to use the bathroom and get a drink. Yeah. Okay. Alright, we back. Damn, I just smashed my hand on the door frame. Ooh, okay, what are we doing? Right, we just wrote out, we can flush a file system. What we need now, we need to like transfer over to user space basically. So let's start thinking about that. Damn, that shit hurt. Fuck. Okay. So let's check out the shell. Let's start with just reading a file. Alright, so right now we have this many syscalls. You have put char, get char, and exit. Read file. What should read file return? Like a pointer to the file data, I'm guessing, and a length. Let's just say, give me So we need to pass like the file name, because it's gonna be like read this file. I'll just say file name for now. It's not lie. And then we need to pass this on. So this is an integer. So we have to like cast this to an integer, which is bizarre. That's why you use file descriptors, I'm guessing. How actually do we want to do this? So on the kernel side, when you hit the trap handler, you're gonna say, hey, it's a syscall. Handle syscall in here. So we're gonna do something like this. Read file. Okay. Damn, do I need more coffee? I'm fucking sleepy. Maybe tea? I can get some tea. So, how are we gonna read a file? We have this trap frame with the arguments. I'm thinking right now, like, do I need to do the so I need to like find the file in the file system. I guess I should do that on the kernel side. So we cast that back to a file name? That seems pretty fucking gross, but alright, we'll try that. I don't know why you're treating these as integers though and not like U32s, but whatever. Alright, so find file, my name, and then like return a pointer to the file data. You could also say read file, give you back like a file pointer and a length. But maybe for now we'll just return like and assume that it's like a null terminated thing. Hopefully, but can we guarantee that it's null terminated? I don't know if we do that right now, do we? I don't think we do. Should we null terminate it here? Alright, now I'm kind of leaning towards read file returning like a file size. File data. Maybe we do something like that. I don't like this. What's his interface for read file? He does a file name, a buffer, and a length. I mean, so it's the same thing except I was gonna return it, but I guess we do this. But why though? It returns the size? You can return the amount written, I guess. A buff and a bufflin. Alright, we're assuming that that's gonna do the deal. File name, bufflin. Okay. Alright, we found the file. Wait, does he do pointer that you can reassign? No. How do we do that? Okay, so I guess I've been thinking about it wrong. You don't return a pointer to the file data, you copy the data into the buffer they provide. So when you say read file, you're saying read this into this buffer, which I suppose makes sense. Okay. So we're gonna mem copy into the buffer this file data that so if you don't have enough space, we're gonna do something else. And you return in a 0, right? Yeah. What should I do? Do I print some shit out? I don't know. So buffer not big enough for a file with size that Alright, so basically all I'm doing is, you gotta cast the arguments to their types. You're gonna go through all the files and try to find a file with that name. So I guess let's just say if F and F in use. Yeah. Okay. Alright, can we compile at all? No member named A in file. Oh shit, we're shadowing a variable name. So the trap frame is named F. So we should call this file. So we'll do that and then fix up this one. Cool, so that one runs, or compiles. Alright, so we can make a syscall. We should probably... Yeah, we don't have a user header. It's just the user space code gets compiled into the stuff. So in the shell, let's do this. Evaluate command line. Read file? Fuck. Alright, we can't do this now. Right, we need like a stir incomp. We have mem compare though, which does have a count. I guess we gotta use that, right? This is gross, but we just don't have enough infrastructure to do this right yet. We need a stir lane. I guess we should just do that. not including the first null character. I feel like it's just that, right? Yeah, that's right. I think... What does Sterling return usually? A size T? So that's right, yeah. Gross. So gross. I don't like this. So we really need to implement like much better parsing for this shell thing too, but for now it's just we want to somehow pull out the so it is zero terminated, so we can't treat it like a string. Actually, we can just do this. Read files plus a space, right? So you want to see read file and then a space. Spaces are tabs. Is there any other types of spaces? I mean, what you really want is space, right? Checks if the given character is either white space, form feed, line feed, carriage return, horizontal tab, or vertical tab. So here's a nice little trick. Let's look up muzzle. They have the best shit to read. Interesting. So this is saying like from tab there's 5 characters up. Where's the like tab? Is it this? 1, 2, 3, 4, 5? Yeah. Interesting. Let's just steal that. Uh-huh. I guess we'll take it as an int. So while that character is a space, advance, just do that like that, yeah. So eat all the spaces, and now the file name, we should have it. So read file name of Bufflin. This is gonna print the buffer's not big enough, or file not found. Okay. I mean, I guess we're just gonna call it. So yeah, read it and print it. Read file. So far I think these have been in common H, right? Syscall? No? So how the fuck does... Oh, because syscall only happens here. Butchar, get jar, read file? I mean, should you have a read file in kernel space? I don't know. I'm trying to avoid as many headers as possible, but it does seem like we need a user space header file. What I don't know is if read file should have a kernel space. Like, we're gonna need to do that? I don't know. Maybe, I mean... No, I guess we'll do this. Alright. Whatever. It's red. File size is in fact these are only 32s. Hold on. Read file. That's gonna return a motherfucking U32. Syscall. Sure, we'll do that. Read file. Yeah. The fuck was I doing here? Alright. So we no longer let's try to read a file. So we have some commands. Read unknown, read file. Jabberwocky. Ah, we don't have backspace, right? I need to fix that. Jabberwocky.txt. Unknown command. Read file jabberwocky.txt. I see. Well, why? Huh. So maybe memcomp is borked? One too many fuckers. Those goddamn off by one errors. Okay. This is kind of expected, right? So we're getting a load page fault when we're trying to load. Is that the address we're trying to load or like the instruction? So we could look at show me like some instructions at this 802.0.1.6.7.8. So we're trying to load this. What? All right. Well, I mean, I didn't really know how to interpret that, but I do know the problem, I think, which is that, you know, we're in user space trying to access memory that's in kernel space. We don't have privilege to do that. Well, let's see. Well, actually, now I'm a little confused because at this point, like, we're in kernel space, right? So the only one who actually accesses it is the kernel, who does this memcopy, and it says, or is it because the kernel's accessing user memory? Maybe that's the problem, is like, even though, like, the kernel has, like, should be able to access user memory, I think you have to say, like, hey, I'm explicitly accessing user memory so that it helps catch errors. And in fact, I think this is what that's talking about. Uh-huh. Trap. Is this the same? We got a D trap. We got a D trap. Stir comp, is he doing the same thing we're doing? Interesting. So they're just not even... Right. Yeah, I just did it a little bit better than that. Like, still shitty, but better than that. Right, it is. So the kernel is accessing a user pointer, so you need to tell the CPU that that's chill. Some permit supervisor user memory access. Do I have a register for that? Or a mask, I mean? A status SPIE. So we need a S status SUM. And which bit is that? Let's look up spec. Actually, I think I have it. Fuck. Is it the privileged mode or unprivileged? Here. Supervisor status register. So it's here. It's bit 18. So this is bit number 18. Jesus. Okay. So the supervisor bit modifies the privilege with which S mode loads and stores access virtual memory. When it's 0, S memory access to pages that are accessible by user mode will fault. When it's 1, they're permitted. Alright. So does that mean I need to like write it before I read and then reset it? Well, shit. I guess I'm gonna have to put a go-to in there. Actually, nah. Nah. What? Will this break the for loop? Or the case? It'll break the inner loop. Yeah. So we're good. So, I guess... So write CSR, the reg and the value. So the reg is status, S status, right? Damn it, I can't just do that. Gross. Okay, so if you have to read it. So you write in there that and a status sum. Then at the end you say not sum. Wait, that's not right. So sum's gonna be something like that. Right, so it's not that. You're gonna have to and it with the inverse, right? So you had this. If you OR it, that means, alright, set this bit. But if you do the opposite and you say and, then it's gonna keep whatever's there and set that to 0. Yep. Okay. Do that, do it. Do that. Do that, do that. Read file. And it reads the fucking file. Boom! Except it starts like halfway through, so that's kind of fucked up. Wait, what? What? So we're like most of the way there, but it starts here. Actually, what happened here? This is weird. It's like... weird. I don't know why that's happening at all. That could be why. Hold on. That actually could be why. Because we were running that flush. Okay, we're good. Yes. Take the W. Alright, new system call, read file. We can read files in user space. That's cool. Can we read the other one? Damn it. Yes, we can do that. That's pretty cool. Pretty cool. Let's revel in our victory for a second. Just gonna see if my dog was there to tell him about my victory. But alas, he is not. Shit, he probably needs to go outside, honestly. Maybe that's a good place to stop. Like, we kind of did the thing. We did part of the thing. There's a bunch of shit we need to, like, work on to clean that garbage up, but I think it's pretty sick that we can read files on the file system now. So let's kind of at least, like, try to explain what's happening. What should I do? Should I like run through like a full run of like system of like operating system boot up to when it reads the file and what's all happening? Or just the read file part? We'll do the whole thing. Alright, so actually, look, even then it's like how far do you go? Let's just look at it all. Okay, so check this out. This is a linker script, which basically just defines the memory layout for the kernel. So, you know, this is where the base address of the kernel is, where it's gonna live in memory. You have your different sections. This is where code is, read-only data, like zero initialized data, rather like non-initialized data, which will get filled with zeros. Stack space and the rest of memory, all in RAM, right? So this just lays out all that memory. Importantly, the stack, this is where the stack's going to be, right? And since it grows downward, this is where it starts. Okay, so that's the memory layout for the kernel. So when you boot, what's happening? Well, first of all, how does it even get to here? Well, SBI is what QEMU hits first. So QEMU is can be built to use SBI, which is like the, what does it even stand for? I know it's like, well, OpenBSI, actually. OpenSBI, sorry. Supervisor Binary Interface is what SBI stands for. So here's the spec for that, which basically just defines like the functions that are like available. It's like the firmware of like a BIOS, right? And so how does it get here? Well, it's the first thing, like it's the beginning. That's all. Like it's just the first bit of code. It's right there. So it goes directly here because this attribute is saying, hey, put this very first in memory. So what happens, it's going to start trying to execute instructions. So the first thing it does is set up the stack pointer. So it's just saying, hey, put this in a register so I know where the stack is, and then jump into this function, kernel main, right? This is just because OpenSBI outputs some information in QEMU, so you give it a space. I'm going to clear the BSS section to 0. That might already happen, but just to be safe, I don't know what OpenBSI does. I could read that, but I haven't. Then we say write into the STVec. This is a CSR, which stands for Control and Status Register. These are like privileged registers in a RISC-V CPU. To control what the CPU does. So one thing is like STVector, this is what's the vector of the supervisor trap supervisor trap vector. That's what that stands for. And vector just means like memory address. It's like the location to jump to. And so you say, here it is, kernel entry. That's the trap handler, which is this. So it doesn't actually go there. It just says, hey, this is, if there's a supervisor trap, this is where you go. Right? Then we initialize the disk, basically, which is a virt.io block device. How much should I go into this? I don't know. It's basically just reading some memory from the device, writing some memory back to say like, hey, here's like what features this supports. We don't even really do that. We're just assuming it works. Yeah. Interestingly, you can read from here the number of sectors. That will be put in a register in that device, so you can say how many sectors are on that device, and I use that to read the whole thing later on. So you initialize the block device, then initialize the file system, which is just like reading the whole block device into memory, and then parsing that into, well, first of all, like tar headers, and then from that parsing it into our own data structure, which is called file. So, you know, we read it all into memory. We parse it into first these tar headers, and then into our file format, right? And you just put that, you just have an array of files. Right now it's a static array of files, so you can have like 32 files right now. Right, so that initializes the file system. Then we set up the processes. So we have this concept of an idle procedure, which is like a null thing. It's like when so one of the tasks of the kernel is scheduling, which in this one is just like you have an array of processes as well, and like here, procs, right? And it just iterates through them, trying to find the next one that's free, like available to run. And if it's available, it'll switch to that one. Through context switching, right? So you have this, what did I call it? Switch context. Yeah, here. So yeah, the way context switching between processes works is like you just are basically saving the context, which is registers and the stack. So you just have to save the call you saved registers, switch the stack, and then, you know, after you swap, you're going to restore the call you saved registers from the process that you're switching to. And then importantly, like the return address, which is the last instruction you were executing before you did a context switch, that also ends up in the context. And so you just jump back there, and now you have switched context. But we have this concept of the idle procedure, which is like, it's like the null one. When you run out of things to do, you hit that one. And Seta implements that one like bizarrely. He has it like as a process, and like allocates memory for it and everything. And I'm just like, no, it's just, you know, I create a single process here instead of running through create. Like I have a stub for it. So if you call create process, it's actually going to like allocate pages and like map them. And take up a slot in the process like array. So like you lose a slot to it, and also like it becomes like, because it's one of the slots, then you have to like offset every other process ID. So I didn't like that. So it's just a dummy one with index -1. And so when you do, so yield is like the call that it does the scheduling, right? Like it goes through the processes finding the next one. And all you do is just say, like, if it's the idle proc, then, you know, you're not going to do a context switch. Easy as. I don't think I'm explaining this stuff very well, but I'm also new to it, so it's not... I myself don't understand it deeply yet. Okay, so yeah. So this create process is creating the process for the shell. Now how does that work? Well, we also have a linker script for user space. We meaning me, because I'm all alone. So user space, every user space program will link this way. So yeah, every user space program will have this memory layout. So, you know, you start at this address and you have all these sections similar, like all the same as, wait, what the fuck is this? Why is the stack in BSS? Is that doesn't seem right. Is it? I feel like this should be like this. I'm gonna go with that. Yeah. Okay. Anyway, so, you start, a user space program starts here, and it's similar to the kernel, right? It just sets up the stack pointer and jumps into main. And so since you see there's no main here, that means every user space program has to define a main. And in this case, the shell is this one. Do I have a shell? Right here, yeah. So here's the main for the shell, right? All it's doing is in an infinite loop, reading a command line, dispatching to evaluate, and then this just switches basically on the command and executes, you know, it just dispatches to each command. Very simple. So one of those commands is readfile. And it'll parse the file name after that and say, call this readfile function, which is just a wrapper around a syscall. Where did the binary shell bin start come from? And size. This just comes from the way that we build this shell, right? So when we compile the shell, we are saying, right, use the user linker script and make a map of the memory and output to this shell elf program, and these are the C files that you compile. Then you're gonna copy it into this bin. So like you just want the raw kind of forget why it does these. Just, I guess because you can't link against an O file. It's like you just want like the raw binary. I kind of forget, honestly. I need to look into that more. But because of the way that this object copy works, this is how the symbols end up getting defined. So if we look in here, binary, oops. Start is here, where we'd expect. But, here you can see it. Binary shell bin start. It's just your calls to obj copy. Like these transformations on the L file turn it into this like shell.bin.o file, which causes this prepending of names to the beginning of it, and gives you these symbols that you can use. All right, rocky, but we're making it through. Okay, so when we create a process for the shell, basically what it does is set up our process data structure, which just has like an ID, which is just an index into the prox array, a state, which is just whether it's running or not, or exited already, its stack pointer, a page table. This is how you map. It has two levels of paging, like so mapping a virtual address to a physical address. So this page table, the first page table, will give you like where to go in the second page table. Then you go to the second page table, it'll tell you like an offset into like physical memory, or rather it's a little bit complicated. So the first page table will give you an index into the second page table, and then using parts of the virtual address you'll get to the second page table, and you'll find the second page table and use the index you found in the first page table, and then that gives you where to go in physical memory, and then you use the offset, which is another part of the virtual address, to give you the actual like physical address. So this is just used to map virtual addresses to physical addresses, and then it has its own stack. So here you can say it's just finding the first unused one and assigning that to be the new process. Here you gotta save. This is just because when you do context switch, it pops all of the so when you do a context switch, you're switching from like process A to process B, and it saves all the registers for A and then pops all of the registers for B. Well, the very first time it enters, it's going to try to pop, and if those aren't set up, then it's just garbage. So this is what we do here. We set those up so that the first time it does a context switch, they're already there, and then the next time it context switches from B to say C, well, the context switch is what does the saving. So you only have to do that here in create process and in context switch. All right, now we're mapping all of the memory. So you know, these different address regions need to be mapped so that the process knows like basically. I can't touch these, I believe, because these are not user accessible. So if like user space does try to, what the fuck just happened? We can hit a page fault. But importantly, here we're mapping all of the user pages. So you're just going through all the memory in this user space program and mapping it to some physical page and marking it as writable, executable, and user accessible. Set up the process here and return it. Kind of understand? And then when you hit yield, this is what starts essentially. How does it start? It initiates a context switch into the first available process. Since there's only one and it's the shell, it'll switch to that process, right? So when you hit yield, it's going to find the first usable process, which is the shell. They're not the same because current is going to be the idle one. So you have to do this fencing so that you can like enable like virtual memory, basically. Yeah. So you do that, then you save the next process stack top at scratch. Right. So this was like a really subtle, important thing. Is that in a trap handler, you can't trust the stack pointer because it could be corrupted. So you need some stable reference to it. And so every time there's a context switch, you store the stack pointer into a control status register. So that's a register that user space can't touch. And so it's safe. So you have a stable reference to this process's stack, like where it begins. And you can see that like handle trap. Where do we use that? Oh, no, it's, well, yeah, kernel entry is the trap handler. Yeah. So the first thing you do is retrieve that. Yeah. So you know that you're not using the corrupted version. Potentially corrupted version. And then, yeah, so once you've done that, you just switch context, which we talked about. It just stores the register, switches stack pointer, and returns to the last place that this process was. And so in this case, in create process, the return address we put in there is where, like, the very beginning of the shell. So you're going to jump to that location, which happens to be right here, main. Oh, sorry, shell. Main. So it jumps here, and boom, now we're executing that process. Okay, so we've got here, we are getting user input, right? I typed readfile jabberwocky.txt. So you're going to evaluate that command line. Compare the first part, it is readfile space. We get the file name, which is jabberwocky.txt. And you call this syscall, which I discussed earlier. Alright, we've fucking gone through the whole thing. Yeah. I described it as best I could. I don't think I did a very good job, but I'm still learning how this system works myself. So I think it'll take time for me to deeply understand how this thing works. But we will do that next time. I suppose. Yeah, peace.